In this lecture, I'm going to define for you the notion of an open set in a general metric space, which I denote here as M, D. So M is our set, and D is the metric on the set. Let's jump right in with some definitions. The first one is going to be the definition of an epsilon neighborhood. So given some number epsilon greater than 0, where typically we think of that as small, the epsilon neighborhood which is a long word, neighborhood. So FYI, in the future, I will abbreviate this NHBD or something very similar to that, NHD. Okay. So the epsilon neighborhood around X in M is a set There are different ways to denote this set. I'm going to call it B subscript epsilon around X. Here, my choice of B is alluding to the word ball. In Euclidean space, we often think of these as open balls. That terminology we haven't even defined yet, but that's where B comes from. And then subscript epsilon, that's like the radius. I'll sketch pictures in a minute, but that's going to be a fixed positive number. And then X, of course, is our choice of point in the metric space. All that to say, that's how I'm going to denote this concept. It's the set of points in the metric space such that the distance from any of these points to X is less than epsilon. So D here is the metric. We say D from X to any member of the set is less than epsilon, strictly less. This is an epsilon neighborhood. All right, with this, we are going to define the notion of an open set in M. For any set A in M, so let me write for any A subset M, or another notational remark I'll make is that my use of the subset symbol here is not strict. Okay, so that just means any subset could even be the entire metric space. For any set A contained in M, we say A is open. If for any choice of point X in A, there exists a choice of epsilon. So I'll use the quantifier there exist. Actually, I shouldn't put a comma here, sorry. For any X in A, there exists an epsilon greater than 0, so that for this X and this epsilon, the epsilon neighborhood around X is a subset of A itself. My markers are really bad. I'd probably pause for a second and go grab some fresh ones. Remark to make is that this choice of epsilon depends on the choice of X. So it could be a different epsilon at different points in the set. Sometimes you'll see epsilon as a function of X or something like epsilon subscript X to indicate that this epsilon number may change if you pick a different point. Okay, let's sketch a brief picture of this. Okay, let's say M, the metric space, is this board I'm writing on. And I'm going to say that this is my set A. You can imagine this like the XY plane because that's probably the most natural way to imagine that this board is a metric space. So we're working in R2 here. If I take an element X from the set, so let's say this one, and say I choose the positive number epsilon to be about this measurement. Sorry, I'm kind of blocking it. It's the same color as my sweater. So I think of this like a radius, because what I'm going to do now is draw the epsilon neighborhood centered at X. Okay, it's very lopsided, but this is the idea of the epsilon neighborhood centered at X of radius epsilon. Okay, so every point inside of this neighborhood has a distance to X, which is less than this radius number epsilon. Okay, so that illustrates the first definition. But now we're interested in whether or not this set A I've sketched is open. Well, the neighborhood I've drawn so far isn't a very nice looking thing to see if you think about the definition of open because I've passed outside of the set A. What we want to be able to do is pick any point in this set and then choose a radius for that point so that the neighborhood I draw around that point with that radius stays inside of A, doesn't cross outside. Okay, so for the point that I chose and the radius that I chose, we didn't illustrate that A is open, but I could have picked a much smaller radius like this one. And that neighborhood does stay inside of A. Coming over here, let's say I pick this point, and we call it Y. Can you imagine drawing a neighborhood around Y of some radius epsilon greater than 0, which stays inside of A? And the answer is yes. Could be about this big. Okay, so that radius would work. A smaller radius would work. Of course, I could pick a radius which is much too large, but we don't need every radius to work. We need for one to work. Okay, this is an open set, and it's not totally clear that I was intending to include what you might think of as the boundary. Boundary is a technical word that we will define later, but your intuition is probably leading you to imagine that this dotted line I've sketched is the boundary. If you play with this picture for a moment, you'll probably convince yourself that my intention with A here is indeed that of an open set. So around any point in this set, we can sketch a neighborhood of radius epsilon which stays inside of A. Okay, let me pause for a moment. I'm going to grab some different markers and also give you a chance to finish writing this down and kind of digest this language before we move on. Let's recap, and then I want to add one more definition before we move on. Our first definition is that of an epsilon neighborhood in a metric space. So for an epsilon neighborhood, you need two things. You need an anchor point A, you think of that like the center of your neighborhood, and a positive fixed number epsilon, which you can think of like a radius. Then we say that the epsilon neighborhood around X is all of the points from the metric space whose distance to X is less than that radial measurement epsilon. So just like in this picture. Okay. Then we defined the notion of an open set. So given your metric space, if you take any kind of subset A, we say A is open if for any choice of point you make in A, like this one, and this one, you can then find a radius epsilon for that point so that the epsilon neighborhood you form around that point is a subset of A. In other words, it lives inside of A. Last thing I want to say before we prove something is kind of a generalization of this first statement. I call this an epsilon neighborhood. If I just say neighborhood, I mean an open set containing a point. So a neighborhood of X, and here I will abbreviate, a neighborhood of an element X from our metric space is any open set containing X. I don't think my marker is better. I'll open a new box. Okay, hopefully you can see that. This is just removing the shape of the epsilon neighborhood that we had in the first definition. So in my picture here, imagining that this board metric space is like the xy plane, all of the epsilon neighborhoods we drew were what you might want to call open disks. Using words like open and boundary in a sort of intuitive way here, we're going to add rigorous definitions to all of those. But the epsilon neighborhoods all took a certain shape. When I just say neighborhood, I mean any kind of open set containing the point. For example, if I take this point X, and given that A is an open set, A itself is a neighborhood of X. So it takes away this prescriptive form of the open neighborhood. I'm alluding to the conclusion of the statement we're about to prove, which is that epsilon neighborhoods are open. So here I said neighborhood is any open set containing. That kind of supposes that that neighborhoods are open, right? But we're going to now prove that this set, the epsilon neighborhood around X of radius epsilon, is an open set. Feels obvious, but it needs to be shown. So we have to show that this set meets this definition. Let's now prove what felt like it should be true as we were talking through those three definitions a moment ago, and that is that epsilon neighborhoods are open sets in their own right. So in other words, if you take any point from your metric space and choose any positive number epsilon to be your radius, then the epsilon neighborhood that you form around X with that radius epsilon is open. So I've taught this statement to students many, many years, and there's always a sense of like, yeah, got to be true, but it's not. So let's talk through it. So here's a series of questions, and after each one, I want you to think about what the answer is. So pause if you need to until you've come to what you would say back to me. So my first question is, what does it mean to say that this epsilon neighborhood, the set B sub epsilon of X, is open? So what does that statement, the epsilon neighborhood is open, what does that mean? Okay, if you got it, it means, so actually let me write that down. B sub epsilon of X is open. It might help as I ask these questions to just think of this as a set A. Sometimes this actual expression makes people think they have more than they do. Okay. This set is open if for any choice of point in that set, well, X is a special point, that's the center. So let me just pick a different letter. So if for any Z in this set, Z has its own epsilon neighborhood that stays inside of the set. So if for any choice of Z, there exists a delta, and here I will drop in the subscript Z to emphasize that first we pick our point, then we pick the radius. And we pick that radius so that the epsilon neighborhood of radius delta sub Z around Z lives inside of the original set. Again, it might be helpful to kind of write this, calling this original set A. Okay, so our epsilon neighborhood is open if for any choice of point we make within that neighborhood, we can then find a radius for that point so that this epsilon neighborhood lives inside of our original set. Okay, how would we show this? So let's say I have a Z and I have an epsilon for that Z, or rather a delta for that Z. How would I show this? Think about that for a moment. Again, these sets have such special form that sometimes it hides what you need to do. If I just said, how do I show that set A is contained inside of set B, you might come to it faster. We need to say, well, any element from the smaller set is an element of the larger set. So that's the second remark I want us to make before we do the proof. And that is this set containment happens if any point from this set lives in this set. So I need to bring in a new name for a point. How about Y? If any Y in is also in the epsilon neighborhood around X. Let me write this symbolically. I think it's clear. So Y in the smaller one, or what we want to say is smaller, means Y is in the bigger one. Okay, so it's set containment, which means show an element from this set has to be in this one. Third question before we start doing the proof itself. Well, how would I show this? So say I've got Y. So I've formed this set. I've grabbed an element Y in it. How do I know it's in this set? That goes back to the definition of this set. So write down an algebraic statement that would tell you that Y belonged to the epsilon neighborhood around X. We have a description for the epsilon neighborhood around x. We said it's a set of points whose distance to x is less than this number epsilon. So that will be our third remark, after which we'll be ready to start looking at the proof. And that is y is in this set if the distance from x to y is less than epsilon. Okay, so it's not a trivial thing. We have to kind of go through this, and we're still not ready to write the proof because it's like, well, let's say I've got z. How do I pick this? So this is really the most important thing, is choosing this number, delta sub z, to be the radius around z that keeps us inside of the epsilon neighborhood around x. How do I pick delta? Once we've picked it, we will just say, okay, we'll grab a point y from that neighborhood, and we'll hope that we can show this. Okay. I think in this situation, it's very helpful to sketch a picture. We are going to imagine again that the board is like the xy plane, and my picture is going to look like a picture in R2, but the argument does generalize, and we write down the proof. It will be a proof for a general metric space. Let's say that we have our epsilon neighborhood around x. So this set is given to us. We've picked an x. Epsilon is a positive number. We don't have to go find those quantities. I'm going to sketch it here so we can leave it up. Here's x. And let's say this lopsided looking shape is the epsilon neighborhood around x of radius epsilon. Okay, that was supposed to be a perfect circle. Okay, this set is just something that exists, right? So this comes to us from the hypotheses of the statement. Now we need to start looking at the z, the epsilon around z that we want to draw, and the y. Okay, so given this picture, let's just pick a random point in this neighborhood and call it z. So let's say that's here. What I want to find is a way to choose a radius around z, which keeps us inside of this epsilon neighborhood around x. I have to do this in a prescriptive way. I need to give you some sort of algebraic statement about this radius so that we know that any point I then pick inside of that neighborhood around z will also be inside of the larger set. That will take us down to point 3. So we must have a recipe for this radius. Here's how, based on the picture, I would start to form this recipe. Let's see, if I were to connect x to the edge of this epsilon neighborhood through z, it looks like that. I know that, in this picture, which again is based in R2, but it will generalize to all metric spaces, that the length of this line segment is this fixed positive number epsilon. But in this diagram, what I've done is break the segment of length epsilon into 2 subsegments. The first one here, the length of that is just the distance from x to z. So let's call it that. The other one doesn't have a name. I want to call it delta sub z. It's really the only thing that I could think to do based on this picture. So if you're like, well, how would you know that that's a safe thing to do? A, we're going to show that it's a valid choice of the radius. And also it's like, this is the only way to proceed. So this here, it's gotta be a good choice of a radius based on the picture. And then algebraically, it will work out. Okay, sorry if you can't read that, but this distance from z to what looks like the edge of our original epsilon neighborhood, this is our choice of radius for z. Something smaller would work too in this picture, but I need to be able to do algebra with the radius that we pick. So I don't just want to say, well, pick something smaller, because I need to be able to write down statements that we can do math on. So what's really nice about this diagram is I can define this radius in terms of 2 other quantities. In particular, delta z is going to be epsilon minus the distance from x to z. Notice that once you've picked your choice of z, this gives you a recipe for the radius. So this adjusts itself automatically to different choices of z in this neighborhood. It's positive. If z is in this neighborhood, then its distance to x, by definition, is less than epsilon. So this number, this subtraction, is going to be a strictly positive number. So we're saying pick a z. Once you've picked the z, this number, the distance from x to z, is defined. Given your z, this is just whatever the metric space tells you that distance is. Do the subtraction, that's your radius. Okay, so the diagram gave us a guide for how to choose this radius. It looks great in this picture. If you imagine drawing this neighborhood around z, kind of ruining my diagram even further, sure does look like it would work for R2. Algebraically, we're going to show in a moment that it works for any metric space. So I'm going to step aside, and when I come back, I'll have erased this. I'll leave up the picture, and we'll finish the proof. It's actually pretty short now that we've done most of the work, which is designing this radius. We're just about ready to write the proof. I should probably mention one more thing before we start writing it down, and that is that once we've got this neighborhood around z, we have to show the set containment. Let me just illustrate on this diagram how to think of that, and then the actual algebra that verifies the set containment will be in the proof itself. So given this neighborhood around z, I want to show that this neighborhood is contained inside of the larger epsilon neighborhood around x by picking any point that we called y in our thought process a few minutes ago. Let's say this point right here. I need to show that for any choice of y, like the one I just made, y remains in the larger set. That gives us set containment. Then we said, well, how will we show that y is in this larger set? We need to show that its distance to x is less than epsilon. Algebraically, that's going to come through the triangle inequality. It just kind of has to. So let's see that in the proof itself. Proof. Again, in the statement, x is given and epsilon is just a positive number. So let's just say that we have those. Given any x in the metric space and epsilon greater than 0, choose some z from the epsilon neighborhood around x. Okay, so we had our starting epsilon neighborhood. I've picked z. This is going to be a fairly concise, direct proof. Sometimes when you're reading written proofs in math, it's like these great steps come out and you don't know where they came from. So all this work that we did, that question and answer session, the diagram, all of that's going to get hidden essentially in the proof because my next sentence is just going to be define this number. So that's why hopefully working through it together gives you more insight to what this proof is actually doing in every kind of step that went into forming this proof. So I'm just going to say, essentially out of nowhere, define delta sub z to be epsilon minus the distance from x to z. Okay, so all that work we did just turns into this sentence. Notice that delta z is positive. I think that's worth pointing out. If you're writing this down and you think maybe later I won't remember why that's the case, you could add as the distance from x to z is less than epsilon. That's straight from the definition of what it means to say that z is in the epsilon neighborhood around x. Okay, so where are we? We have picked a z. We've already got this neighborhood. So again, all that work we did really just came into one sentence. Now this neighborhood is set in the picture. What we now need to do is say, okay, consider any y in this neighborhood. Consider any y in the neighborhood around z of radius delta z. Okay, I've now dropped this point into the diagram. It remains to show that the distance from y to x is less than epsilon. Notice, I think I'm going to do this on one line. in part to save vertical space. The distance from x to y, I want to say that this distance from x to y is less than epsilon. Just like in the picture where I said there's really only one way to proceed, same story here. There's only one way to proceed with this computation. Y is kind of random. I don't really know, even in this picture I've drawn, where I should put y. So how do I relate it to x? I go through their mutual friend z. So the only thing I can do, the only way to proceed, is with the triangle inequality and compare each of these individually to z. We can relate both of them to z. We can't relate them directly to each other. So this is less than or equal to the distance from x to z plus the distance from z to y. That's triangle inequality. The distance from x to z is less than epsilon, and the distance from z to y is less than delta z. I'm just thinking I could say this is less than epsilon, this is less than delta z, which is epsilon minus xz, but actually I'd end up then with 2 epsilon minus dxz. So I think what I'm going to do is just leave this as it is. And I'm going to say strict inequality here and go up in size by saying that this distance right here is less than the radius of the neighborhood that y lives inside of here. So that's less than delta z. Okay. Continuing to the right just to fit the proof on the board. Let's now use equality and just replace delta z with its literal definition. Okay. So again, we could have actually bounded this above by epsilon, but there was no need because now we can say explicitly that the distance from x to y is less than epsilon. So as you read this, you're like less than or equal to, less than preserves it, so it's less than. So the distance from x to y is less than epsilon. Interpreting this algebraic statement, we conclude that y is in the epsilon neighborhood around x. Thus, y is in this epsilon neighborhood around x, which shows us set inclusion. I'm going to say, and therefore, this set is contained in this set. I've done a set inclusion proof. We are just about done, but I think at this point, it's useful to take a moment to pause, digest what we've done, and then decide for yourself, where are we? Like, what was even the goal? I think in this kind of proof with all the steps we did, the diagram, you can lose sight of what we're actually trying to show. So just take a moment, remember what we were trying to show, and then we will wrap it up. Before I write one more sentence and draw a little conclusion box, let's recap what we were doing. We wanted to prove that in any metric space, an epsilon neighborhood is open. So given x and some choice of positive radius epsilon, the set b sub epsilon around x, this epsilon neighborhood is an open set. To prove this is an open set, we needed to show that it matched the definition of an open set. That was definition 2 a moment ago. We said a set was open if, for any point in the set, you can find a radius for that point so that that new epsilon neighborhood stays inside of the original set. And that is exactly what we have done. We've said, given this set, choose a random point in it. Here's a radius, which is positive, that defines an epsilon neighborhood around this point that stays inside of the original set. We have now shown that this set matches or meets the criteria to be open. Since it's a definition check and it's a direct proof, I think I can wrap this up quickly. So let's say, hence, this set is open. Okay, sorry, squeeze that in there. So I want you to take out of this a couple of things. One is don't take what feels intuitively true in topology for granted. We defined epsilon neighborhoods. We defined open sets. If I want to say that an epsilon neighborhood is an open set, I have to show it matches the definition of being an open set, and that is what we did here. So that's one thing, is don't just fall back on intuition. Use rigor. This was rigorous. Other remarks to make: always remember what the definitions are, right? So to show that it's open, I needed to show the definition was being met. Maybe we have other theorems later, but it's like if all I have is the definition, I need to meet the definition. Diagrams are helpful. When you're working in a metric space, pictures you draw on paper that might look like you're working on R or R2 can be illustrative. They could perhaps only tell you something about Euclidean space, but in this particular example, the diagram gave us something that worked in general in any metric space. So this computation here did not rely on the metric space being R2. So sketch pictures as you work through topology. Make diagrams, sketches. Keep in mind that you might be working in a general setting, but something like visualizing it in R2 can still help you. And then maybe one more remark before we move on. That is that, look at this triangle inequality, make sure you understand every step we took. Otherwise, yeah, I think we're ready to be done with this proof, and we'll keep going with open sets. Let's take a break from rigorous proof writing to work through some examples. So all of these examples are in Euclidean space, and most are just on the number line. For each of these examples, let's determine if the set is either open or not open. Do not say closed. In mathematics, open and closed are not antonyms. They're not sets are not like doors. They're not either open or closed. If something is not open, that's not the definition of closed. So leave the word closed completely out of this discussion. So each of these sets is either open or not open. Let me go ahead and work through the first one right away. And then for each of the other ones, I will give you a moment. You can pause, work out what you think the answer should be on your own, and then I will give you an illustration of why it's either open or closed. For the first one, we have the set that we like to call the open interval from 0 to 1. We've been calling this open interval, you may have called this open interval for years without ever defining the word open. Turns out that's okay. It is open. Let's do two proofs, if you will, or at least illustrations of why it's open. Okay, let's say this is the number line. We're working on R, and I am looking at the open interval from 0 to 1. So I'm going to sketch it like this. What does it mean to say that this set is open? Go back to the definition. It means that if I take any point from this set, like say this one, I can find a radius epsilon to draw a neighborhood around that point, which stays inside of the set. Let me kind of illustrate that here on R. So let's say this is my radius. What are all the points on the number line within distance of this radius of x? Sorry if I said that kind of funny. Forms an open interval, right? Okay. So it looks like this. So in R2, it looked like an open disk. Here, it's like an open interval. So all of these points are within this distance of x. Okay, so what we could do, again, I'm going to give you two arguments here. What we could do for the first argument is say how to choose the radius epsilon for any choice of x, kind of like giving you a recipe like we did in the proof a moment ago. I'm not going to write out a full description here. I'm just going to give you the recipe. So given x in this set, choose epsilon sub x to be, I'm going to base my description off of the picture. What I did is I looked at x and I looked at which number it was closer to, 0 or 1. In the picture, it was closer to 1. So I was like, okay, what's this distance? And then I cut it in half. So I'm going to say 1/2 of whichever distance is smaller, x to 0 or x to 1. So that's the minimum of the distance from x to 1 and x to 0. Distance in Euclidean R on the number line is the absolute value. So this expression means the distance from x to 1. So either that or this. Okay, couple of remarks. One is that this 1/2 here is optional. You could let this radius go all the way up to 1 here. Okay, that would still give you a neighborhood that stayed inside of the original interval. This is flexible and it adjusts itself. This choice of minimum here means that if I move x over here, it's going to flip, and we would be saying, okay, let's compare this and cut that in half. Okay, so this is a formula for a choice of epsilon that would work given any point in the original interval. Okay, so that was argument 1. Argument 2 is faster, and that is this interval, the way it's given to us, could be rewritten as an epsilon neighborhood, one particular epsilon neighborhood. So let me just put it over here. Or this set is actually the epsilon neighborhood of radius 1/2 centered at 1/2. So let me just write that here. So it's the epsilon neighborhood of radius 1/2 centered at 1/2. So that's argument 2. We proved that any epsilon neighborhood in any metric space is open. So as soon as I recognize that this interval is this epsilon neighborhood, we're done. We know it's open. Okay, so that was an illustration of the first set here. This is the open interval from 0 to 1. Wouldn't be too hard to generalize this to the open interval from A to B, where A is any number less than B, right? So open intervals are open is what I'm trying to get to. Let me step away for a moment, pause if you'd like, and work out the second example. Example 2, the answer is not open. So let's sketch this. Just like the picture above, except this time we're including the point 0 in the set. Okay. If I want to show that the definition of open is not being met by this set, then I need to say, well, what would it mean to negate the definition of open? When we said a set was open, we said that for any choice of point x, you can find a radius that will work. If I want to negate that, then I just need to say there's one point for which there is no radius that works. There could be more than one, but you just need to find one point which does not allow you to draw an epsilon neighborhood around that point, which stays inside of the original set. Okay, so looking at this picture, if I feel like it's not open, how do I choose that point? Well, based on the work we just did, we know that anything over here, we could use a similar construction to form a neighborhood that's going to stay in this set. Obviously, it's 0 that's the problem. Okay, so I want to show that because of the existence of 0 in this particular set, this set is not going to meet the definition of an open set. Okay, so let's do this precisely. Imagine I've taken any epsilon greater than 0 because we have to establish that all possible radii will fail. Well, the epsilon neighborhood around 0 is going to look like this. What's the problem? The problem is the left side, right? We cross out of the set. That's what it looks like to not be open. I think I can write out essentially a rigorous argument with one phrase here. Choose any epsilon greater than 0. Notice that the epsilon neighborhood that you then define centered at 0, I want to say it crosses out of the original set. I think what I'll do is I'll take the intersection of this neighborhood and the complement of our starting set. Here I'm saying the complement of this set, not the complement of the intersection. This is non-empty because it has all of the points between negative epsilon and 0. As this intersection, sorry, struggling to write. Actually, the intersection is literally negative epsilon to 0. Epsilon is greater to 0 than 0, so I know that negative epsilon really is to the left of 0. So this is a non-empty interval on R. Therefore, this neighborhood is not a subset of the original set. And that's enough because epsilon was arbitrary. So what I'm saying is every possible epsilon neighborhood that you would draw centered at 0 cannot be contained inside of the original set. So this is not a point where we can find an epsilon neighborhood that creates a set that stays inside of the original set. Okay. All right, so that set was not open. What about the third example? Again, let me give you a moment to think about this one on your own. For this third example, we have the open disk of radius 10 around the origin. There I've kind of used the conclusion in my description of it. You can draw a picture kind of like this. It's harder to come up with a description of a choice of epsilon that will allow you to meet the definition of an open set. So I'm going to take the shortcut and recognize that this set can be viewed as an epsilon neighborhood and therefore must be open. So in particular, this is the epsilon neighborhood around the origin in R2 of radius 10. Okay, think about Rn, the entire metric space Rn. So imagine I'm working in some general Rn. Is Rn an open set or not? Yes, it is. Here's a proof. For any x in the metric space in Rn, the epsilon neighborhood around x of radius 3 stays inside of Rn. And that's enough. It's open. Okay, so I just made an arbitrary choice of a radius here. You could have picked 1, say like the unit ball, if you will, around x stays inside of Rn. But this is the argument. If I say that I'm working in Rn and Rn is the metric space, keep in mind that that means that, if I take any point, it's in the metric space. So if you say we're working in this metric space, there are no points involved which do not belong to the metric space. So as soon as I draw a neighborhood in the metric space, the neighborhood is in the metric space. We don't leave the metric space. Okay, these next two examples, you might want to do them together. So think about rationals and irrationals as subsets of the number line. Neither of these is open. And the one-word explanation is density. Let me say what I mean by that. Okay, so I'm going to argue these at the same time. For any real number x and any positive number epsilon, if you draw an epsilon neighborhood around x, you are going to pick up infinitely many rationals and irrationals. Okay, so that's kind of taking both at the same time. Let me address them individually now. I'm trying to write less uphill. Okay, so if I wanted to do these one at a time and give you a really good argument, I would say, let's start with rational numbers. Let x be any rational number. So I want to take any member from the set of rationals. If x is a rational number and epsilon is greater than 0, and I then draw the neighborhood of radius epsilon around x, I'm going to pick up an irrational number. In fact, I'll pick up infinitely many, but you just need to pick up one. As soon as I picked up an irrational number, I conclude that the set I drew left the set of rationals. So no epsilon neighborhood around a rational number can stay within the set of rational numbers because it must have irrational numbers, but also vice versa. So if y is an irrational number and epsilon is a positive number, positive choice of radius, then the epsilon neighborhood I would draw around the irrational number y would pick up at least one rational, in fact, infinitely many rationals, and therefore cannot be a subset of irrational numbers. Okay, so to conclude, we've got an open set, a not open set, an open set, an open set, and two not open sets. Let's now look at two examples, one at a time, from spaces which are not Euclidean spaces. For our first non-Euclidean example, let's consider R2, the xy plane, with the taxicab metric. Then the set A is going to be like a vertical strip. So let's sketch it. Here's R2, roughly. And then A is the set of points whose x coordinate is between 1 and 2. So let's say this is x equals 1, and this is x equals 2. So this is the set A. Is this an open set? Certainly, if we were working in regular Euclidean space with the regular Euclidean metric, you probably want to say yes. I said certainly, but hopefully your inclination is to say yes. If I were to pick this point and draw, say, a little disk around it, I could pick a radius small enough that would keep my disk within these two vertical lines. So yes, it's open with respect to the regular Euclidean metric. What about the taxicab metric? Well, for that, you might realize that our notion of an open set is going to look different. We're actually also going to conclude that this is open, though. So a taxicab circle looks like a diamond, which means that a taxicab epsilon neighborhood is going to look like the interior of the diamond. Okay, so I'm gonna draw one that works. Okay, I don't know if you can see this, but it's an open diamond around this point, which is actually touching over here at x equals 2, by keeping us between these two vertical lines. Okay. I don't want to write out a full proof here that this is open, but here's the idea. Given x in the set, choose your epsilon to be. Actually, you know what? I should be careful here because x sounds like a point in the set, but it also sounds like the x coordinate of an xy point. So why don't I call this P? Okay, so what I'm going to do is name this point P and say it has xy coordinates, x comma y. There we go. Okay, so be careful. Choose epsilon sub P to be the minimum of the distances between the x coordinate and x equals 1 or x equals 2. So this is like a lateral distance. I'm going to describe it with absolute values. So this x coordinate, measure its distance to 2, the right side of the set, and also its distance to 1. Pick the minimum so that we get the smaller of the two possible radii that these two quantities measure. And then if it's the smaller of the two radii, it will work for the line it's closer to it, and which will make it work for the one that's farther away. Okay, this is how you could define an epsilon that will work for any choice of P. I'll leave it to you to write the full proof. Let's move on to looking at a metric space, which really does look quite different. For our final example in this lecture, let M be any set, for example, a set of markers I have, and let D be the discrete metric. So this is this binary metric that measures whether x and y are the same. So we say the distance from x to y is 0 if they are the same element, so like the same marker. Otherwise, the distance is 1. We know that this is a metric. Given this metric space, experiment with it. Try to work out what open sets in this metric space look like. So are there open sets? Which ones are open? Just play around with the ideas, and then I'll come back and we will finish this lesson together and we'll talk about what's coming up. What I hope you did for the past few minutes was take a set, for example, the set of pink markers, and just imagine what it would mean to apply the definition of an open set to this set. So if I take a member of this set Can I draw a neighborhood around it that stays inside of this set? Well, what does a neighborhood in the discrete metric space even look like? Okay. The answer, if you got there, may have surprised you. And the answer basically is that every set in a discrete metric space is open. That's worth writing down. Let me prove it for a non-empty set at least. So suppose A is a non-empty subset of M. So I'll write, suppose A subset M is non-empty, and let X be an element in A. Can I create an epsilon neighborhood centered at X which stays inside of A, doesn't contain anything from the complement of A? And the answer is yes. You just have to pick the right radius. You could actually go all the way out to 1, but to make it really clear what's happening, let me pick a radius of 1/2. Notice the epsilon neighborhood around X of radius 1/2 consists of every member of this discrete metric space whose distance to X is less than 1/2. Revisit the definition of a discrete metric. If you are X, your distance to X is 0. Anything else, the distance is 1. That's bigger than 1/2. So the only thing in this epsilon neighborhood is X itself. So it's a single element set, and X is an A. So this is a subset of A. That means that for any element in A, I can design an epsilon neighborhood that stays inside of A. So A is open. Okay. This is really cool. It's different than Euclidean space, right? So with Euclidean space, we were easily able to find sets which were not open. If you revisit the taxicab example from a moment ago, if you dropped solid lines basically at x equals 1 and x equals 2, that would produce a set which was not open. I cannot do that in a discrete metric space. Every set in a discrete metric space is open. I want to wrap up this lecture here, but I also want to mention what's coming up next. I've said every set in a discrete metric space is open, but then I also specified in my proof that I was looking only at non-empty sets. Turns out the empty set is always open in any metric space. That's something that we will prove in the next lecture, which is going to be a shorter lecture. We are going to look at the entire metric space, which we kind of already discussed with Rn, the empty set, and then ways to take open sets and consider either their intersection or union. So that will be our next lesson.